Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into a realm where space folds in silence, time bends like drifting wind, and gravity becomes not just a force, but a whisper of something deeper. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the mystery of black holes and the hidden geometry of the universe. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. Let's begin not with a bang, but with something softer, something before light, before gravity, before even the ticking of time. Imagine, if you will, a moment that isn't a moment at all. No seconds ticking forward, no distance stretching between stars, just potential. Not even darkness, because darkness requires the absence of light. And here, light itself hasn't been born. There's no sound, because sound needs air, and there is no air. No things, no space, no when. It's hard to picture a beginning that doesn't begin in time, isn't it? Every thought we have has a before and an after, but the universe may have begun in a way that defies that kind of thinking. Physicists call it a singularity, a point not in space, but of space, not in time, but of time, a kind of fold in the very fabric from which reality would be stitched. In this singularity, all the energy and matter that would one day become stars, galaxies, coffee cups, and your favourite playlist, everything, was packed into a kind of timeless compression. Not a dot in the sky, not a speck in a void, but a state where the rules we know simply didn't apply. Not yet. And then, in an act not of explosion, but of expansion, the universe began to unfold. The Big Bang wasn't like fireworks in the sky. It was space itself growing from the inside out. Imagine blowing up a balloon, but instead of the balloon expanding into something, the balloon is the something. There was no outside to expand into, just the fabric of the universe stretching, curling and blooming into being, and along with that space, time itself began to tick. Not from a divine clock on the wall, but as a natural rhythm of unfolding. Time was born as the measure of change, the silent count of events, the space between a cause and its effect. From that moment forward, every second you've ever experienced is part of that original pulse. For the first 380,000 years, the universe was hot. So hot that light couldn't travel freely. Photons, those tiny packets of illumination, were constantly scattered by free-floating particles like fireflies in a sandstorm. But eventually the universe cooled. The particles slowed and atoms could form, mostly hydrogen, the simplest building block of everything. When that happened, light was finally able to travel unimpeded. That ancient light is still moving through space right now, gently stretched by the expansion of everything, like the soft ringing of a bell that was struck 13.8 billion years ago. Scientists call it the cosmic microwave background. You can think of it like the afterglow of the universe's first breath, a faint, cool light that whispers from every corner of the cosmos, even in the quiet between stars. If you were to hold out your hand to catch some of that ancient glow, you wouldn't feel it. But it's there, passing through you, every second. Your body, your room, your planet, bathed in light older than galaxies. That background radiation is not just a relic of the past. It's a reminder that even in silence the universe hums. Even in darkness, it remembers how to shine. Now that atoms had formed, gravity began its quiet work. No longer fighting against endless energy, it could begin to gather. Slowly, delicately, matter started clumping together, drawn by the soft pull of gravity's hand. Clouds of gas drifted toward one another, and over millions of years those clouds became dense enough to ignite. The first stars flickered into life, not with the roar of a flamethrower, but with a steady bloom of light. They were enormous and strange, fusing hydrogen into helium and in time into heavier elements, each one a furnace sculpting the periodic table. And when those stars died, because everything, even stars, must someday fall, they collapsed, not into nothing, but into something new. Some of them became black holes, and black holes aren't holes at all. They're not voids, not destruction. They are what's left when gravity wins, when the structure of space folds inward so tightly that escape becomes impossible. Not even light, the fastest thing we know, can break free. But we'll get to that. For now, just hold this in your mind. Everything you are, everything around you, was once light and energy. And before that, folded silence. From timelessness came time. From formlessness came form. And from the quiet potential of nothing came a universe filled with galaxies, atoms, dreams, and you. You're not outside this story. You're made of it. You're one of its sentences, a soft syllable in a poem still unfolding. Let's continue. Now that the universe had begun its quiet expansion, and light had been set free to wander the young cosmos, the story began to change tempo, not faster, but more intricate. The early simplicity of hydrogen gas clouds drifting in a vast cooling space gave way to complexity. Gravity, patient and precise, began its long, slow choreography. And from that gentle gathering of matter, stars were born. It's easy to forget how strange a star really is. From our safe distance, the sun seems familiar. Warm, constant, a bright shape behind morning curtains. But a star is not just a glowing ball of gas. It's a delicate balance between outward pressure from fusion and inward pressure from gravity, like a tug of war that holds perfectly moment by moment for billions of years. Within the cores of these stars, hydrogen atoms, once free-floating in the great post-Big Bang ocean, began fusing into helium, releasing light and heat. It is through this process over vast stretches of time that the universe started forging the elements needed for everything else. Carbon, oxygen, nitrogen. These were not present in the beginning. They were sculpted inside stars, in fusion reactions running hot and slow, and heavier elements like iron, gold, or uranium. Those required something even more dramatic. A star, even in death, continues to give, because no star lasts forever. When massive stars exhaust their fuel, they lose the ability to push outward. Gravity, always waiting, takes over. The star collapses inward with such force that the core may implode in a single moment. What happens next depends on the star's mass, but the result is always transformation. Sometimes this collapse leads to a supernova, a brilliant, brief bloom of light that can outshine entire galaxies. Other times, if the star is massive enough, it goes further. It collapses so completely that it no longer becomes a thing in space. Instead, it becomes a place where space itself is altered, a black hole. And here we pause, because the term black hole is misleading in its simplicity. It sounds like a hole in a wall, something you might peer into or toss a coin into and hear no echo. But that isn't what a black hole is. It is not a hole. It is not even a place, strictly speaking. It is a region, a shape in space-time, where the pull of gravity has become so intense that no path leads out, not even for light. Let's stay with that image for a moment. Light, the fastest traveller in the universe, the very embodiment of speed and motion, cannot leave once it crosses a certain boundary. That boundary is called the event horizon. It isn't a wall, or a shell, or a physical surface. It's more like a threshold, an invisible contour drawn by the rules of gravity. If you cross it, you cannot return. Not because something grabs you, but because all possible futures point inward. And yet, from the outside, a black hole doesn't look violent. It doesn't swirl or burn or scream. It doesn't give away its nature easily. In fact, the area just outside the event horizon can be calm. If you were orbiting near a black hole, safely outside the horizon, you might not feel much at all. The stars would look strange. Time would flow oddly. But nothing in particular would seem to shout that you were near one of the most extreme objects in the universe. It's this quietness that makes black holes almost poetic. They are not cosmic monsters tearing through the galaxy. They are shadows, silent, immense, and folded. They are the end state of matter gone dense enough to change the structure of reality itself. And yet, despite their mystery, black holes are common. There are likely millions in our galaxy alone. Some are just a few times the mass of our sun, left behind by once massive stars. Others are unimaginably large, supermassive black holes, millions or even billions of times more massive than the sun, sitting quietly at the hearts of galaxies, including our own. Yes, at the very centre of the Milky Way is a supermassive black hole called Sagittarius, a star, a compact giant around which our entire galaxy orbits. And it does not devour the stars around it like some hungry beast. It simply exists, influencing everything through its quiet gravity. You might think of a black hole as a kind of monk, silent, still, cloaked in robes of darkness, seated at the centre of things, pulling gently but inexorably on the world around it. It doesn't need to speak to be felt. The journey of matter, from hydrogen gas to star to black hole, is a kind of cosmic meditation on transformation. Nothing is wasted. When a star dies into a black hole, it doesn't vanish. It becomes part of something more abstract. The information it once held, the way atoms were arranged, the energy in its motions, isn't erased, at least not entirely. Physicists are still debating what happens to that information, and we'll come to that soon. But for now, it's enough to say that black holes aren't ends. They are transitions. In fact, if you look at the universe through this lens of gravity and light, time and transformation, you start to see it not as a place made of objects, but of flows. Everything flowing, changing, becoming something else. Stars give birth to heavier elements. Those elements make planets. Planets give rise to life. Life builds telescopes. Telescopes look into the darkness and see the shadows left by ancient stars. There's something comforting about that. About the way nothing is truly lost, just folded, rearranged, waiting. In the next session, we'll step closer to the event horizon itself, that boundary beyond which no return is possible. What does it mean to cross it? What would you feel? What would you see, if anything? But for now, let your thoughts drift like stardust. The stars are not burning for no reason. They're crafting the very fabric of existence, one fusion at a time, and from their deaths, black holes are born, not with violence, but with silence. Gravity is one of those things we rarely think about unless we trip over it. It holds your coffee mug to the table, guides the arc of a tossed apple, and keeps the moon loyal to Earth. It presses you gently into your mattress every night, like a quiet hand reminding you that you belong here, that you're part of something weightier. And yet, for most of history, we thought of gravity in very practical terms. A force that pulled, a kind of invisible string tugging on things with mass. That idea worked well enough to explain falling apples and planetary orbits, to draw maps of the solar system and launch rockets skyward. But gravity has always been more than a force. It is a bending, a warping, a subtle reshaping of the stage on which reality unfolds. Albert Einstein's general theory of relativity, published in 1915, offered a way of seeing gravity not as a pulling agent, but as geometry itself. Mass and energy curve space-time, and that curvature tells other objects how to move. It's a poetic reversal of how we used to think. In this view, the Earth doesn't orbit the Sun because it's being pulled by an invisible string, but because the Sun has created a kind of dimple in the fabric of space-time, and the Earth, like a marble on a curved surface, follows the natural lines laid out beneath it. To visualize this, you might imagine placing a bowling ball in the center of a stretched-out trampoline. The ball sinks slightly, and any smaller objects placed nearby will slowly spiral toward it, not because the ball is actively pulling them, but because the very fabric beneath them has changed. Now imagine that trampoline in 4 dimensions, and the ball isn't just bending space, it's bending time too. This bending of time is not metaphorical, it's real. The closer you are to a massive object, the slower time moves. Not slower as in perception, but slower as in literal passage. Your seconds are longer, your heartbeat ticks through more stretched intervals. This isn't science fiction. It's been measured and verified, not just with satellites, but with GPS systems that must account for time dilation to work accurately. Clocks on satellites tick slightly faster than those on Earth because they are farther from Earth's gravity. Even the small difference in height between your head and your feet means that time is passing ever so slightly differently for each. This phenomenon, gravitational time dilation, is one of the most quietly mind-bending aspects of modern physics. We think of time as universal, as something that happens evenly everywhere, but the universe disagrees. Time, like light, bends around mass. It stretches, curves, delays, and nowhere is this more extreme than near a black hole. As you approach a black hole, space-time curves more and more steeply. From the perspective of a distant observer, someone watching you from afar, your movements would appear slower. Not just sluggish, but stretched. If you were to fall toward a black hole, they would see you inching closer and closer to the event horizon, the boundary beyond which nothing returns, but never quite reaching it. From their perspective, time slows so dramatically that you appear frozen at the edge, a ghostly image fading into redder and redder light, smeared across the horizon like an echo of your former self. But from your own point of view, nothing would feel particularly odd, at least not until much later. You would fall as you always fall, accelerated by gravity, pulled inward by curvature, and if you passed the event horizon without being torn apart, you might not even notice crossing it. The boundary is not marked. There is no sudden jerk or flash or wall. You would pass through it as easily as you pass through the air, but with one important difference. Once you cross it, all paths point inward. The escape routes disappear, not because you're trapped in a prison with bars, but because space itself has been restructured so that every road leads toward the centre. This isn't just a poetic image, it's a precise mathematical truth. The directions inside a black hole are rearranged. Even if you pointed your spaceship's engines directly away from the centre and fired them with full force, the best you could do is delay the inevitable. It's like being caught in a river that grows stronger the further downstream you go. At first you can paddle against the current, but eventually the water flows faster than you can swim, and the current carries you along. Inside the event horizon, time itself becomes like that river, and the centre, the singularity, is where that current ends. Black holes, then, are not monsters or vacuums or cosmic garbage disposals. They are more like waterfalls in space-time. From a safe distance, they shape the motion of stars and dust. They bend light. They keep quiet company in the centres of galaxies. But up close, they are places where the structure of reality begins to strain and twist, and where time itself behaves in ways that challenge our intuition. Even the term falling into a black hole carries a kind of misleading urgency. The fall is not violent unless you're near a small one, where the tidal forces are strong enough to stretch you lengthwise, something whimsically called spaghettification. In a larger black hole, like those at the centre of galaxies, The tidal forces at the horizon are weak enough that you might cross the boundary without even realizing it. Only later, as you drift further inward, would the stretching begin. It would not feel like being ripped apart. It would feel like being drawn towards something that refuses to let go. The pull of gravity here is not just a downward force. It is a reshaping of how motion and time must work. Every step you take, every direction you aim, still moves you inward. There is no ground, no wall, no bottom, just a directionality of experience that always points toward deeper curvature. The laws of physics don't disappear, they remain in place, but their geometry is turned against you, and so gravity, which once pressed your feet gently into the earth, becomes something far more profound. Not a force, but a structure. Not a string pulling you down, but a slope in the fabric of everything. And that slope, near a black hole, becomes steep enough to change what time means, what direction means, even what survival means. In our next session, we will step even closer to the event horizon and ask, what happens when you cross it? What would it feel like to surrender to that slope? And why, from the outside, do you never seem to fall all the way in? But for now, let yourself rest in the idea that gravity is not just something that pulls. It is the quiet shape of presence, a soft hand curved into space-time itself. There are boundaries in the universe that feel more like whispers than walls, not the kind you can touch or see, but ones that mark a change in how the rules work. Boundaries that don't stop you with a jolt, but instead rearrange what's possible. The event horizon of a black hole is exactly that sort of boundary. It doesn't shout. It doesn't block your path. It simply marks the place where all futures point inward, where every road curves toward a centre that never allows return. The name itself, Event Horizon, carries a quiet beauty. A horizon, as we usually think of it, is a line between sky and earth, a shifting edge that defines what we can see. But this horizon isn't about sight, it's about causality. It marks the boundary beyond which events can no longer influence the outside world, a one-way surface. Once something crosses that line, its story is no longer available to those who remain on the outside. And yet, this horizon has no surface, no texture, no hardness. You wouldn't notice when you crossed it. If you were in a spacecraft falling steadily toward the black hole, all your instruments might still behave normally. The stars around you would distort and stretch, but they do so gradually. There's no sudden alarm that goes off, no line painted in space to warn you that a profound shift has occurred. You wouldn't feel a bump. You wouldn't see a flare. You would simply continue moving, but now into a future that has no exit. From the outside, however, things look very different. To a distant observer, someone watching your descent with a telescope, the approach to the event horizon appears to slow. Your ship's motion would become sluggish, your radio signals delayed, red-shifted into deeper and deeper tones, until eventually they fade entirely. Your image, too, would linger near the horizon, growing dimmer, stretched into a smear of ever fainter light. In a sense, you'd never be seen crossing. You'd appear frozen just at the edge, caught in a kind of suspended fall. This isn't a trick of distance or equipment. It's a consequence of how time behaves near the horizon. The curvature of space-time becomes so extreme that the clocks of those falling in and those staying behind diverge dramatically. For you, time moves forward as always, but for those outside, your fall stretches into an eternity. The event horizon becomes not just a boundary of space, but a boundary between different experiences of time. You might imagine light itself playing along this edge, struggling to escape. Photons that are emitted just outside the horizon can spiral outward if they're lucky enough to be aimed just right. Others circle the black hole, trapped in looping orbits at what's called the photon sphere, a fragile balance where light dances on the edge of forever. And those emitted just a bit too close. They curve inward, drawn past the horizon, gone from the universe's visible stage. This moment, when light can no longer escape, when paths collapse inward, when even the fastest thing known is held captive, is what defines the black hole. The event horizon is its outer signature, the last footprint of escape, and yet, paradoxically, it's not a wall. It's not something a black hole builds. It's something space-time builds around the black hole, a contour, not a cage. There's a quiet elegance in that idea. You can't touch the event horizon, but it touches everything. It's a boundary that behaves like a mirror for what we cannot know. Everything that falls beyond it becomes invisible, not because it vanishes, but because its light can no longer reach us. The event horizon isn't where things end. It's where our ability to see them ends. To linger at that edge is to consider something profound. This isn't just about black holes. It's about how knowledge itself has limits, and how those limits aren't always brutal or sudden. Sometimes they're soft, like fog rolling in, like a door that closes silently behind you. And if you cross, there's no way to call back. You become part of the interior, and the universe outside continues on without you. But what if the information carried by what falls in, its structure, its arrangement, its identity, could still linger in some way? What if, even though nothing escapes, the horizon itself could act as a kind of ledger, quietly recording what it absorbs? We'll return to this idea later when we talk about the strange notion that black holes might be libraries, not dumpsters. That they remember, in curvature and whisper, even what they consume. For now, rest with the image of the horizon, not as a danger or a final moment, but as a passage, a quiet line in the cosmos that behaves like a door that locks behind you. You don't hear it click, you don't feel the knob turn, but once it closes, the path back is gone. And yet, from inside, you continue. The fall feels smooth. You drift inward, deeper into the curved fabric of space-time. The centre grows closer, not in space, but in inevitability. There is no surface to crash into. There is only the surrender of options, like stepping into a story that cannot be retold to those who remain outside. In the next session, we'll follow that path. What does the journey feel like once you've crossed the horizon? What happens to your sense of space and time? What stretches, what remains, and what disappears? For now, though, stay with this thought. The horizon is not an end. It is the beginning of elsewhere. Imagine you're falling toward a black hole. Not with panic, not with chaos, just drifting steadily, as if drawn by something more like gravity's invitation than its command. Your ship has passed the point of hesitation. The stars behind you have stretched into streaks. Ahead, there is no clear destination, no floor, no wall, only a deepening of direction. You've crossed the event horizon. From your perspective, strangely, nothing special has happened. Your instrument still hums softly. The dials still tick. You don't feel heat or crushing pressure. You don't pass through a membrane or bump into anything solid. And yet, you know something has changed. You're now in a region of space-time where all roads, no matter how forcefully you try to steer, lead inward. This inwardness is not just about movement through space, it's about time too. The very structure of cause and effect has shifted. Inside the event horizon, moving away from the black hole centre is no longer a spatial direction. It's a temporal one. Just as you cannot move backward in time outside a black hole, you cannot move outward once inside. The singularity lies ahead of you like tomorrow. Unreachable perhaps, but inevitable. Outside, however, your story looks very different. For an observer watching your descent from a safe distance, you appear to slow as you approach the horizon. Your ship dims, its light stretched into longer, redder wavelengths. You move slower, frame by frame, as if the film of your fall is being played back with ever-widening pauses. Eventually, your form seems to freeze in place, fading slowly into the darkness, never quite crossing over, at least not from their point of view. This haunting asymmetry is a feature of relativity. Time does not move the same for all observers. Near the immense gravity of a black hole, time itself stretches. From your own point of view, you fall smoothly, but from the outside, your descent takes longer and longer, so long in fact that it might never appear to complete, as if the black hole is slowly swallowing your image, one frame at a time, until there is only a faint glow where you used to be. Back inside, your journey continues. The curvature of space-time deepens. The shape of everything becomes more focused. This isn't a tunnel or a cave, it's more like falling inward through possibility itself. And as you fall, something else begins to happen. The gravity begins to act differently on different parts of you. If you're oriented feet first, your feet are closer to the singularity than your head. That means they are being pulled just a little more strongly. The difference might start small, but as you fall further, it grows quickly. This is what physicists call tidal force, not in the sense of ocean waves, but in the sense of gravity changing rapidly over short distances. On Earth, the moon causes tides by pulling slightly more on the side of the planet facing it. Near a black hole, this effect becomes extreme. The gravity is so intense and changes so sharply with distance that it begins to stretch objects along the direction of the fall and compress them side to side. The result is something rather whimsically known as spaghettification. A person or object falling into a small black hole would be stretched into a thin, elongated shape, like a noodle. But despite the playfulness of the term, the process is not violent in the way you might expect. There is no explosion, no sound, no flash. The stretching is part of the geometry of space. It unfolds as calmly as any other rule of motion. In fact, if you were falling into a supermassive black hole, the kind that sits at the centre of galaxies, the tidal forces at the event horizon would be weak. You might pass through without noticing much at all. The stretching would only become significant much deeper inside, closer to the singularity. This means that, in principle, you could experience the crossing peacefully, a quiet slip into a realm where the rules have changed, but not your experience of motion, at least not yet. What you'd see as you fall is harder to predict. The light from the stars behind you would continue to distort, wrapping into strange rings and arcs around the black hole silhouette. You might witness what's called the Einstein ring, a glowing circle caused by light from stars directly behind the black hole being bent into a full loop. As you fall further, the outside universe might appear to speed up, play forward in flashes. Since your time is slowing relative to theirs, you could, in theory, glimpse the far future, a universe racing on without you. But these sights would be short-lived. Deeper inside, light from the outside world would be less able to reach you. The curvature would begin to isolate you from everything. The black hole would start to feel less like a place, and more like a boundary around memory itself. You're still falling. But now, you're falling alone. And yet, there's something strangely serene about that. You're not being crushed, not being torn apart, at least not yet. You're being guided by space-time itself, as if riding the fabric of a dream that pulls gently inward. There is no sound. Sound requires air, and there is none here. There is only motion and silence, the kind of silence that fills up space between thoughts. Eventually you would come to a place where the curvature is so extreme, the equations describing motion no longer make sense. The singularity, a point, not in the sense of a location you can reach, but as a place where our understanding breaks. Not a physical dot, but a collapse of description. The laws that guided your fall, the coordinates that charted your path all begin to fail. Not because the universe has ended, but because our tools for measuring it have. In our next session, we'll rest in this strange interior, a place beyond the horizon, where reality folds so tightly it becomes unreadable. A place where physics is quiet, and perhaps so are you. But for now, imagine yourself still falling, not fast, not afraid, just calmly moving inward, stretched between moments, like a memory sliding out of reach. Now you are inside, beyond the event horizon, past the point where any signal could be sent back, deeper than light itself can reach. The outside universe, with all its stars and swirls, its seasons and clocks, has fallen behind, not vanished but gently disconnected, like a voice in a dream fading as you wake up into another one. There is no turning around, no pausing. Forward is no longer just direction, it is destiny. And yet somehow everything feels still. Stillness inside a black hole is not the kind we usually imagine. It is not the stillness of a pond at dawn, or the hush after snowfall. It is a stillness born from geometry. Inside, space-time has curved so completely inward that every path, no matter how you twist or turn, leads to the same conclusion. It's as if the floor of reality has sloped downward, and every thought, every breath, every tick of your inner clock is following that slope, unable to climb out. You're not falling through space anymore. You're falling through time itself. What does that mean exactly? Outside the event horizon, time and space behave as we expect. You move through space, and time ticks forward beside you. Inside, the roles are reversed. The singularity, the dense core at the centre of the black hole, is not a location you can manoeuvre around. It is a moment in your future. Just as you cannot stop Tuesday from arriving, you cannot stop your arrival at the singularity. You may twist, you may accelerate, but every path, every motion is just a different way of going forward in a time that ends there. And yet, this is not a collapse in the emotional sense. There is no panic here, no explosion, just inevitability. You might picture yourself drifting slowly, like a leaf caught in an invisible current. The laws of physics still hold, though they begin to stretch. Your surroundings do not tear apart, at least not immediately. If this black hole is large enough, supermassive, like the one at the centre of our galaxy, the tidal forces might remain weak even far inside. You could survive the descent at least for a while. You could observe. You could think. But what would you observe? There is little light now. Anything that crossed the event horizon before you has either moved, ahead, or was distorted beyond recognition. You are alone, or seem to be. The walls of the universe are no longer transparent. You're inside a place where the definitions of place begin to dissolve. You could try to describe what you see, but your words would begin to falter. You might say the stars have vanished, that the sky has curled in on itself, that the world is falling with you, or maybe that it no longer exists at all, and perhaps all of those would be true. This is where our understanding begins to tremble. At the heart of the black hole lies what we call the singularity, a point not of size, but of incomprehensibility. According to the equations of general relativity, the curvature of space-time becomes infinite here. Densities rise without limit. The structure of reality as we know it collapses into something that our math cannot model, that our minds cannot hold. It is not a place where atoms can be. It is not even clear whether place means anything here at all. And yet, the singularity is not necessarily a thing. It may be rather a signpost, a way for our equations to say, we've gone as far as we can. Beyond this, the language breaks. The coordinates fold in on themselves. The metaphors go silent. The black hole does not speak. It folds. What happens here? That remains one of the deepest questions in physics. Some believe that a quantum theory of gravity, still uncompleted, would soften the singularity, replace it with something finite, describable. Others suggest that the singularity might not be the end at all, but a bridge, a connection to something else, a white hole perhaps, or another universe entirely. There are ideas, equations, proposals, but none that the universe has confirmed to us yet. Perhaps that's the most humbling part, that in this silent centre of mass and time, we reach the limits of what science can currently say. not because we lack imagination, but because the tools of observation and prediction, so sharp elsewhere, begin to blur in this place, and what remains is not knowledge, but wondering, a kind of reverent curiosity. Inside the black hole, you would not know all this, at least not consciously, but you might feel it in a metaphorical way, a sense that the very fabric of what can be spoken is fading into something that can only be experienced, like music that slows until it becomes one long note, like language that stretches until only breath remains, stillness, not just in motion, but in meaning. And yet, something extraordinary might be happening even now, though you can no longer signal outward, and no one can see you fall. It's possible, just possible, that everything about your journey is still being written somewhere, that the horizon behind you is encoding your information, preserving the shape of your story in the slow glow of radiation, that somewhere, far outside, long after, the black hole will begin to whisper again. But we're getting ahead of ourselves. For now, we rest in the fold, in a region where physics hesitates and thought drifts unanchored. The journey into a black hole is not a tale of noise and violence, it is a meditation, a long silent inward motion toward a truth that may be unknowable. And if the singularity truly is the end, then it may be the quietest end the universe has ever allowed, not with a bang, not with a scream, but with a stillness so complete that even time gives up its ticking. In our next part, we'll change our direction, not by leaving the black hole, but by thinking differently. We'll explore how black holes, despite their silence, might still speak, through heat, through information, through the strange language of entropy and light. But for now, breathe. You're in a place where questions rest, where motion continues without direction, and where the edge of knowledge feels like floating. There's a quiet river that flows through everything. You can't see it directly. It doesn't rush like water, or sing like wind, or leave a visible trace across the sky. But it moves, always, from then to now, from order to disorder, from the possible to the remembered. We call it entropy. And it's not just a scientific term. It's a hidden current beneath all experience. It's why the tea on your desk grows cold, why houses decay, why memories fade. It's the reason you remember yesterday but not tomorrow. Entropy is, in its simplest form, a measure of disorder. But more precisely, it's a measure of how many ways a system can be arranged without changing what it is from the outside. A deck of playing cards, fresh from the box, has very low entropy, only one or two neat orders. But shuffle it once, and already there are more possible arrangements. Shuffle it 100 times, and it becomes something else entirely, not because the cards have changed, but because their order, their story, has dissolved into countless possible versions. In physics, entropy explains the direction of time, not as a force, but as a preference. The laws of nature don't demand that time move forward, but entropy does. It makes forward more likely than backward. There's no law saying shattered glass must stay broken. But the number of ways glass shards can be scattered is so much greater than the number of ways they can be assembled into a perfect cup that the cup once broken never reassembles. Entropy tells us which futures are probable, and those are the futures we live in. Black holes, strange as they are, obey this rule. In fact, they elevate it to something more profound. You might think a black hole being so simple, just a dark sphere, defined by its mass, spin and charge, would have very low entropy. But that's not the case. A black hole has the highest entropy of any object of the same size. It's a paradox, a thing that looks like nothing, that shows no surface or structure, that devours all variation and noise, is in fact the most disordered object imaginable. It was Jacob Bekenstein who first proposed that a black hole should have entropy. Stephen Hawking, sceptical at first, later confirmed this idea through quantum theory. What they discovered is astonishing. The entropy of a black hole is not proportional to its volume, as you might expect from a normal object, but to the area of its event horizon. That smooth, silent surface, that invisible shell where light is lost, becomes the ledger of disorder. The bigger the black hole, the more information it could potentially contain, but that information is smeared across the edge, not stored within. What this means is subtle, but powerful. Black holes don't break the laws of thermodynamics, they reveal them more deeply. Like a hidden truth folded into silence, they continue to obey the rules, even when it seems they shouldn't. Entropy doesn't vanish when matter falls in. It increases. The black hole's horizon grows. The surface becomes richer, more encoded, more full of unknowable arrangements. You can think of it like this. The black hole doesn't erase the story of what fell into it. It simply compresses it into unreadable form. Like a library that has been locked and buried, the pages still exist. You just can't open them anymore. And yet, entropy has always been about loss. Not of matter, but of pattern. A black hole doesn't destroy atoms necessarily. It hides them. But it hides their relationships, their structure, the connections that once made them meaningful. If you drop a book into a fire, the carbon atoms remain. But the arrangement, the words, the sentences, the story, disappear into heat. That is entropy. Not annihilation, but unweaving. And entropy does not wait for black holes to appear. It touches everything. The cells in your body, the light in your room, the memories you hold that are slowly changing each time you recall them. Every system drifts, not toward chaos, but toward what's more probable. That doesn't mean purpose is lost. It means that order is rare and precious and temporary. The arrow of time, that feeling of forwardness you experience every day, is tied to entropy's direction. You feel it not because clocks tick, but because your brain remembers one direction and not the other. Because you can see the past but not the future. Because the universe as a whole began in a state of extremely low entropy and has been drifting gently and unrelentingly toward higher entropy ever since. Why did it start that way? No one knows. The early universe was smooth, orderly, strangely pristine. The reasons for that beginning remain a mystery. But black holes sit at the far end of that arrow waiting. They are the entropy sinks of the cosmos, the places where order falls and does not return in any recognizable form. They are not violations of thermodynamics. They are the purest expressions of it, and in that way, you are connected to black holes too. Not because you are destined to fall into one, but because your life, your warmth, your thoughts are part of this long unfolding. You're a temporary arrangement of low entropy, a ripple in the flow, a structure that will, in time, return to noise. And that's not a sad thought. It's a reminder that your existence, ordered, breathing, remembering, is rare. And in its rarity it becomes beautiful. Just as a flame is made more precious by the darkness around it, so is your awareness made meaningful by the sea of disorder it briefly resists. In our next session, we will meet the whisper that black holes give back, the slow, ghost-like radiation predicted by Hawking, a kind of unspooling, a breath that continues even after all else has fallen silent. But for now, just float with the idea that everything changes, and that change has a rhythm, a one-way river that carries not just stars, but you. Imagine a silence so perfect it seems complete, a silence that has swallowed stars, light and sound, a silence that is not merely the absence of noise, but the presence of something deeper, a kind of quiet that feels final. That's the silence we usually associate with black holes, and yet even here, at the edge of the ultimate stillness, something is happening. Not loudly, not urgently, but persistently, with a kind of patient insistence. The black hole whispers. It was Stephen Hawking, in the early 1970s, who first suggested that black holes might not be entirely silent. At the time, this was a radical idea. According to classical physics, black holes could only grow. They absorbed matter and energy, and nothing ever escaped. But quantum mechanics, always the quiet troublemaker, whispers a different story. To understand it, we must visit the edge again, the event horizon, not as a barrier, but as a stage. According to quantum field theory, the vacuum of space is never truly empty. It seethes with activity. Even in the quietest regions of the universe, particles and antiparticles constantly wink into existence in pairs, borrowing energy briefly from nothing, only to annihilate one another almost immediately. These virtual particles are a natural part of the quantum sea, flickers that usually cancel each other out before anyone notices. But near a black hole's event horizon, something strange happens. Suppose a pair of these particles appears right at the edge. One of them might fall inward, past the horizon, while the other escapes into space. From the outside, it looks as though the black hole has emitted a particle. It looks as though it is glowing faintly in the dark. This is Hawking radiation. The process is subtle, almost ghostly. The radiation is incredibly faint, so faint that it has never been directly observed. For a typical black hole, it's far weaker than the background noise of the universe itself, but in theory, over an unimaginably long time scale, this radiation adds up. The black hole loses energy. It shrinks, slowly, steadily. It evaporates. This is where the whisper begins. The black hole, which once devoured everything that came near, now begins to give back. Not in the same form, not as the stars or particles it swallowed, but as heat, as entropy, as radiation. Over time, the horizon contracts, and the black hole grows smaller. In the final stages, as its mass dwindles, the radiation becomes more intense, until eventually it may vanish entirely, leaving behind only a trace in the cosmic background. This changes our image of black holes dramatically. No longer eternal prisons, no longer silent, immutable voids, they become temporary, finite, decaying. Still strange, still extreme, but now with lifespans and endings. But that leads to a deeper question, one that continues to stir debate even now. If a black hole evaporates, and the information that fell into it was truly lost, doesn't that violate the principles of quantum mechanics? According to our best theories, information cannot be destroyed. It can be scrambled, changed, buried, but never erased. So if black holes truly vanish, what happens to the information they consumed? Some physicists believe that Hawking radiation, faint as it is, may carry traces of that information. That in its delicate glow, encoded in ways we do not yet understand, lies the structure of what was once inside. Not in full form, not like a photograph or a transcript, but like the whisper of a memory. Others propose that the information remains preserved on the event horizon itself, a kind of cosmic ledger, written in curvature and light. This is known as the black hole information paradox, and it remains one of the most profound puzzles in modern physics. Because if black holes destroy information, our understanding of quantum mechanics must change. But if they don't, then we must find a mechanism, some hidden hand, that preserves it through the slow, soft voice of radiation. It's tempting to imagine that each escaping particle, each faint wisp of Hawking radiation, carries a sliver of story. A piece of what was once complex, now simplified into heat. As if the black hole is not dying, but releasing, slowly and reluctantly, the memory of everything it has ever known. Not all at once, not clearly, but over time, like embers releasing warmth long after the fire is gone, like a sigh that lasts for eons. And perhaps that's the beauty of this theory, not just in its scientific implications, but in its emotional resonance. The idea that nothing is truly silent forever, that even the darkest, most distant parts of the universe may someday speak again, that even the most final of endings might in the end be a transformation. Because Hawking radiation is not just about loss, it's about return, a slow undoing, a giving back, not in the same language but in echoes. It says, the black hole does not vanish in rage or collapse, it fades gently, it dissolves in light. And if this is true, if black holes evaporate, if their silence ends in heat and their secrets melt into whispers, then we have reason to hope. Hope that nothing is ever truly erased, that even the most unimaginable mysteries may one day be understood, that the universe, in all its vastness, has ways of remembering. In our next session, we'll step deeper into this mystery, into the strange and beautiful idea that information might not reside inside the black hole, but on its surface, that the edge of things may hold the key to what lies within, and that what falls into darkness may still leave behind a map, etched not in stone, but in light. But for now, rest with this image, a black hole, once thought to be a silence without end, slowly glowing at its edge, faint, patient, and purposeful. Not screaming, not mourning, just whispering endlessly into the dark. There's a strange thought that keeps returning in the quiet corners of theoretical physics, a thought that reshapes our understanding of space, of memory, and of what it means for something to be kept. The thought is this: perhaps the information that falls into a black hole is not lost inside, but preserved on the surface, not written in ink or etched in grooves, but encoded in the very fabric of space, the event horizon as a kind of shimmering page, recording everything it touches. This idea began with Jacob Bekenstein's realization that black holes must have entropy. Stephen Hawking took it further. If black holes emit radiation and shrink, then their surface area, the size of their event horizon, must decrease too. But since entropy is tied to surface area, that surface must be meaningful. It must be doing something more than hiding what falls in. It must be storing something. That's where the Bekenstein-Hawking entropy formula comes from. It tells us that the entropy of a black hole isn't proportional to its volume, as we might expect, but to its surface area. The skin, not the interior, is what counts. Every bit of information that enters, a planet, a particle, a thought carved into atoms, is somehow reflected in the horizon's area. It's as if the black hole's edge stretches slightly to make room for each new entry, not to reveal it, but to remember it. This leads us to one of the most poetic and mind-bending ideas in all of modern physics, the holographic principle. A hologram, as you might know, is a two-dimensional surface that encodes a three-dimensional image. You tilt it, and the picture shifts, giving the illusion of depth. It's a trick of light and storage, but in the world of black holes, and perhaps in the universe at large, the hologram may be more than a trick. It may be the truth. The holographic principle suggests that everything inside a black hole, the mass, the energy, the information, is actually encoded on its surface. That the interior is, in some sense, an illusion, or at least a projection of information stored on the boundary. The event horizon becomes a kind of information skin, a library with no bookshelves, just surface, no text, just curvature. But everything that was, somehow still is. This doesn't mean that people, planets, or photons survive in recognizable form. It means that their patterns, the way they were arranged, the laws that describe them are imprinted, like delicate creases on a folded page. You wouldn't recognize the story by looking at the wrinkles, but in principle it's there. The black hole becomes not a tomb, but an archive. This idea, while astonishing, isn't limited to black holes. Some physicists believe that the entire universe may be holographic, that everything we experience in 3 dimensions may be encoded on a 2-dimensional boundary somewhere far beyond our reach. The laws that govern us, the particles that form us, the gravity that holds us, they might all be shadows, projections, echoes of something simpler on a distant screen. Of course, this is still theoretical. No telescope has yet seen the edge of the hologram. No measurement has revealed the folds of information encoded in a black hole's skin. But mathematically and metaphorically, the principle fits. It resolves paradoxes, it preserves information, and perhaps more importantly, it changes how we think about space and about what it means to be remembered. Because that's really what's at the heart of this. Memory, not in the conscious sense, but in the cosmic one. A black hole that remembers not who you were, but how you were arranged. Not your thoughts, but your trajectory. Not your face, but your formula. A memory so abstract it barely feels like one, but a memory nonetheless. And it invites a gentle reflection. What does it mean to be remembered by the universe? Not as a person, perhaps, but as a pattern. Not as a name, but as a contribution to curvature. Maybe this is the quiet legacy of matter, that even after it's fallen, even after it's gone from sight, its presence lingers as part of the fabric itself. You might imagine the event horizon not as a mouth that consumes, but as a mirror. Not one that reflects your face, but one that reflects your presence. A sheet of space where the story doesn't vanish, it just becomes unreadable, folded, encoded, compressed. And if this holds true, if the horizon is a kind of recording surface, then the black hole is not a place of forgetting, but of concealment. It keeps what it takes. It does not destroy, it stores. And it might even slowly leak that information back through radiation, as we saw in the last session, in pieces, in riddles, in softened warmth. Of course we don't yet know how to decode such a library. We don't know the language, we can't open the book. But just the possibility that the book exists at all is a quiet triumph. It means that the universe is not wasteful. That information, even in its most obscure form, is precious. And maybe that's the deepest comfort in all of this. That black holes, which once stood as symbols of finality and erasure, may in fact be places of preservation. That in the darkest regions of the cosmos, where no light escapes, a kind of record-keeping continues. Silent, slow, relentless. In our next part, we'll widen the view. Because black holes don't sit alone in the universe. They move, they collide. And when they do, they send ripples through space-time itself. Gravitational waves, carrying the echoes of ancient mergers. But for now, let this image settle in your mind. A dark sphere, not blank, but full. A horizon that holds stories. A boundary that does not speak, but remembers. Imagine folding a piece of paper so that two distant dots, once separated by space, now kiss in quiet proximity. You draw a line through the fold, and suddenly what once required a long journey becomes a single step. That's the metaphor often used to describe a wormhole, a bridge, a tunnel, a shortcut through space and time. But unlike paper, space cannot be folded so easily. And yet, the equations, softly humming in the background of general relativity, suggest that such folds might exist. These hypothetical structures are known as Einstein-Rosen bridges, first proposed in the 1930s by Albert Einstein and Nathan Rosen. In their mathematical form, a wormhole connects two regions of space-time, like a tunnel bored through the fabric of the cosmos. If you were on one end and someone else on the other, in theory, you could pass through and emerge elsewhere. Not just in another location, but perhaps in another time. But like most things that sound too wondrous to be real, wormholes come with caveats. The Einstein-Rosen bridge solution collapses too quickly for anything to travel through it. It's unstable, like a soap bubble in a storm. Without something to hold it open, something exotic and unknown, it pinches off before even a single atom can pass through. The math allows the idea, the universe so far does not. Physicists have proposed that exotic matter, material with negative energy density, might stabilise a wormhole, keeping it open long enough for a journey. But exotic matter is not just rare. It may not exist in usable form, and even if it did, the energies required would be immense. Still, the idea lingers, not because it's practical, but because it's beautiful. You might imagine a wormhole not as a violent tear in space, but as a quiet fold. Not a rupture, but a bridge. A hallway lined not with doors, but with gravity. On one side, this world, this now, this sky. On the other, something else. Perhaps another part of the same universe. Perhaps another universe altogether. Some theories suggest that every black hole could be paired with a white hole, a mirror twin that expels what the black hole swallows. In that pairing, a wormhole might form, a tunnel from one region of space-time to another. In this view, a black hole is not a dead end, but a passage, a beginning, not just an ending. But here again, theory and reality part ways. White holes, while mathematically possible, have never been observed. If they exist, they are shy things, hidden or fleeting. Perhaps they only lived at the birth of the universe. Or perhaps they exist, but not in our frame of reference, like echoes from a conversation we were never part of. Even so, the thought persists that somewhere in the tangled folds of space-time there may be shortcuts, not highways, not wormhole portals from science fiction, but gentle folds, passages that open and close like thoughts, that exist not for convenience, but as artifacts of deeper structure. Wormholes also raise strange questions about causality. If you could step through one and arrive in a different time, could you change the past, or become trapped in a loop, revisiting the same moments forever? These aren't just narrative puzzles, they are real concerns for physics. Time, like space, is curved by gravity, and wormholes, if they exist, might twist time so tightly that its usual direction begins to bend back on itself. But before we go too far into loops and paradoxes, we return to the present, to what is known, which is this: wormholes are not forbidden. They are permitted by the same equations that describe planets orbiting stars and apples falling from trees. Their existence is not impossible, just unconfirmed. Like a door drawn on a dream. You can see its outline, imagine its handle, feel the wood beneath your palm. But when you push, it's still a wall. And yet, even that possibility holds power. The idea that the universe might allow such passages, even briefly, even rarely, expands the space of what we consider real. It reminds us that the known world, as vast as it feels, may be only a room in a much larger house. That beyond what we can measure lies a region of soft questions, ones that science doesn't reject but hasn't yet answered. In the gentle light of such thinking, wormholes are not shortcuts. They are metaphors made of math. They are reminders that space is not flat and simple, but curved and dynamic. That the distance between 2 points may not always be what it seems. That sometimes the path from here to there is not a line, but a fold. And if they do exist, hidden in quantum foam or at the hearts of black holes, they may never be navigable, but they don't have to be. It is enough that the universe allows them to be dreamed, that its rules, so often strict, make space for possibility. In our next session, we'll stay with the idea of bent time. We'll ask what it means to walk in circles through causality, and what it might feel like if, after falling into a black hole, you didn't just end, but arrived. But for now, rest with this image: a bridge that may never be crossed, a tunnel that may never be opened, and the quiet suggestion, written deep in the math of the cosmos, that space itself may contain not just places, but paths. Time, for most of us, is a one-way path. You wake up, eat breakfast, walk through your day, and fall asleep under a sky that's just a little different from the one before. Clocks tick forward, hair grows, fruit ripens, then spoils. We live inside time like fish live in water, surrounded by it, shaped by it, barely aware that it is a substance at all. But what if time weren't a straight river? What if, under certain conditions, it curled back on itself like a ribbon in the wind? in the strange geometry around black holes, this question is not just poetic, it's mathematical. General relativity allows for solutions called closed time-like curves, or CTCs. These are paths through space-time that loop back to their own beginnings. In such a path, an object, or perhaps a person, might return to a moment they had already experienced, not by reversing time, but by following it. Just as you might walk in a circle and arrive where you started, CTCs are time circles that bring you back to the same moment, again and again. These curves are not science fiction. They emerge naturally in certain space-time geometries, particularly around rapidly spinning black holes. The mathematics sees they could exist. The physics, however, is more cautious. To create such loops requires not only intense gravity, but also conditions we don't yet know how to replicate. Energy densities, rotation speeds, and structures that stretch our imagination and our credibility. But let's allow ourselves just for a moment to dwell in the possibility. Imagine falling into a black hole. Not the quick fall into a stellar remnant, but the smooth descent into a spinning giant, a Kerr black hole which rotates rapidly, twisting space-time like a spoon in honey. As you descend, the curvature of space-time doesn't just grow, it begins to swirl. Directions become uncertain. Time begins to tilt. Somewhere in this rotating geometry, the equation suggests that it might be possible to enter a region where your path loops through time. You wouldn't notice a sharp turn. There would be no sudden shift, no cinematic flash. Time would still seem to pass forward for you. Your heartbeat would keep its rhythm, but the sequence of events around you might begin to repeat. You might find yourself in a moment you've already lived. Not déjà vu, but return. Of course, this raises strange questions. If you could go back, could you change things? Could you prevent your own fall? Could you interfere with the chain of events that brought you here? Physics answers cautiously. Most interpretations suggest that causality protects itself, that the universe won't allow contradictions. What happens, happens. And if time loops back, it loops consistently. You might find yourself in the past, but only if your presence there had already been part of that past. The loop is closed not just in space, but in logic. And yet, what would it feel like? If time bent that way, if your journey through a black hole brought you not to an end, but to a point behind you, or beside you, or folded within you, what would it mean for memory, for identity? Would you recognize the repetition? Or would it simply feel like another moment, no more unusual than yesterday? Some physicists suggest that these closed curves might allow for something like time travel, though not in the way films imagine. Not machines with glowing buttons, but natural passages created by gravity itself. Routes through warped space-time that connect one moment to another, not through speed or illusion, but through curvature. The same way a straight line across Earth eventually brings you back to where you began. It's important to say that these are possibilities, not predictions. We have no evidence that time loops exist in the real universe. We have never seen a closed time-like curve, nor observed anything that requires one. But the math allows it. And that allowance, that quiet permission, gives us space to wonder. Perhaps the black hole is not a hole at all. Perhaps it's a fold, a region where the fabric of space and time tucks into itself. A place where the future bends toward the past, not because of choice, but because of geometry. Where beginnings and endings lose their separation. Where stories do not proceed, but recur. In such a place, existence becomes a circle, not static, not frozen, but eternal in motion. Not a loop of boredom, but a spiral of becoming, each cycle echoing the last, yet subtly different, like ripples from a stone dropped again and again. And if that's true, if time can curve, then perhaps the real mystery is not whether we could travel through time, but whether we already are. Whether memory, with its half-reconstructed scenes, is a kind of time travel. Whether the act of imagining the future is not prediction, but participation. whether every choice, every echo, every pause in thought is part of a loop we can't yet see. In our next session, we'll lift our eyes from the curve and ask, what if the black hole doesn't just bring us back to this universe, but leads elsewhere, to another space, another set of laws, another unfolding of time? But for now, let this idea settle. That time, like space, may not be a line, but a shape. And in the heart of a black hole, that shape may bend until it meets itself. Imagine standing at the edge of a black hole, not on the outside looking in, but on the inside looking somewhere else. Not back toward the place you came from, not toward the singularity you were once falling into, but toward a space that feels unfamiliar. The physics here is no longer firm beneath your feet. Time has warped into near silence. Space has folded into shadow. And yet, you wonder, what lies beyond? Could there be an other side to a black hole? The idea sounds like fantasy, but in theoretical physics it has been seriously considered. Some models suggest that black holes might not end in destruction, but in creation, that the singularity, this point of infinite curvature, where space and time collapse into unknowability, could, under the right conditions, lead not to a final stop, but to a beginning, a spark, a bounce, a rebirth. This is where the notion of black holes as birthplaces of new universes arises. It's speculative, certainly. We have no direct evidence, but the idea sits gently on the edge of several theories: loop quantum gravity, certain cosmological models, and aspects of inflationary theory. What they suggest is that, instead of collapsing into nothing, the matter inside a black hole could undergo a transformation, emerging as a new space-time bubble, disconnected from the one it came from. A new universe, budding from the old like a flower blooming in the dark. Think of it like this: the matter falling into a black hole doesn't reach an end. It reaches a kind of bottleneck, a place where density and pressure and energy become so intense that the known rules no longer apply. And just as the Big Bang may have been a singularity from which our universe emerged, perhaps the singularity inside a black hole serves a similar function, not as a collapse, but as an expansion, but inward, or outward, or elsewhere. This leads us to the concept of a multiverse, not just parallel dimensions stacked beside each other like books on a shelf, but a vast, possibly infinite field of bubble universes, each with its own physical laws, constants, and possibilities. Our universe may be one of many, and black holes, far from being endpoints, might be the portals through which new ones are seeded. This isn't science fiction. It's one of the predictions of eternal inflation, a cosmological model in which our universe is one expanding bubble in a frothy sea of inflating space-time. Each bubble forms its own universe. Each birth is like a cosmic breath, carrying its own geometry and rhythm. And some researchers wonder, could the formation of a black hole be one of those breaths? Could what falls in here reappear there? If so, what would it feel like to cross? The answer is, we don't know. We may never know. Because if a new universe does form beyond the black hole's boundary, it would be causally disconnected from ours. You wouldn't be able to send a signal back. You wouldn't emerge and report. You wouldn't fly into a black hole and come out in some other galaxy. Instead, you, or whatever remained of you, would become part of that new cosmos. You would be the dust of its stars, the structure of its galaxies, the breath of its beginnings. And yet, even without the promise of travel or return, the idea carries a certain peace, that what seems like an end might be a transformation, that the collapse of matter into darkness could be the seed of something else. Not an echo, not a mirror, but a new unfolding. Some have described this as the ultimate recycling program. Matter collapses in our universe, and through processes we barely understand, emerges elsewhere, reborn, not preserved in form, but preserved in essence, not remembered as a shape, but as a possibility. Perhaps your atoms become part of a sun. Perhaps the information of your fall becomes a ripple in time, an echo that shapes the rhythm of something that is yet to dream. One poetic phrasing sometimes used in this context is that black holes are not graves but gardens, places where what we thought was gone begins again, not in the same soil, not in the same light, but with the same ingredients, reshaped, reimagined. And the seeds, those things we feared had been lost, were never lost at all. They were simply planted where we could no longer follow. There's humility in this idea. We may never access these other universes. We may never know whether they exist. But the possibility reminds us that we are not the centre of things, that our view, as vast as it feels, is limited, that mystery still dwells beyond the horizon, and in that mystery perhaps something beautiful is growing. It invites us to reconsider how we think about endings, not just in physics, but in life. A black hole, once feared as a void, becomes instead a womb, an unknown that carries within it not absence but potential, not silence, but a whisper beginning to form. And perhaps, in this moment of quiet, as we drift near the edge of speculation, that's all we need. The possibility that every fall contains a future, that what bends may also bloom, that space, even at its darkest, might be more generous than we expect. In the next part, we'll listen for those echoes, gravitational waves, rippling through the fabric of space-time, carrying with them the signatures of black holes colliding, merging, singing. But for now, linger with this image. A black hole dark and distant, not as an end, but as a seed. The universe folding into itself and then, in silence, beginning again. Imagine two black holes, ancient and massive, slowly spiralling toward each other in the vast darkness of space. For millions, perhaps billions of years, they've danced this slow, invisible waltz, circling, drawing nearer, wrapping space-time around themselves like folds in silk. And then, one day, they collide. Not with fire or sound, not with a bang that could be heard like thunder, but with a ripple, a tremor, a vibration that moves not through air but through space itself. In 2015, scientists at LIGO, an observatory built with unimaginable precision, detected such a ripple, the first direct observation of gravitational waves. For the first time, we didn't just see the universe, we heard it. Not in the way our ears understand sound, but in the way space-time understands motion. Two black holes, locked in embrace, sent a wave outward that travelled across galaxies, across eons and lightly brushed against Earth. That brushing, that subtle deformation of space itself, was enough for LIGO to register the event. The universe had sung, and we were listening. Gravitational waves are ripples in space-time caused by the acceleration of massive objects. When black holes merge or neutron stars collide, or when cataclysmic dances unfold on cosmic stages, space-time doesn't stay still. It shivers. These ripples stretch and squeeze the very fabric of the universe as they pass through. Not enough to tear or break, but enough to record, enough to whisper. And the beauty is, they carry memory. Each wave tells a story about mass, about spin, about movement and momentum, about the lives and deaths of stars. It's as if the universe keeps an archive not just in light but in motion, not just in what it shows, but in what it hums. You're made of stardust, yes, but also of story. Every atom in your body was once inside a star. Some were forged in supernovae. Some drifted through interstellar clouds before coalescing into planets. The oxygen you breathe, the calcium in your bones, the iron in your blood, all of it born in ancient furnaces. And long before those stars collapsed, they themselves were formed from waves, density ripples in the early universe, seeded by quantum fluctuations just after the Big Bang. Those ripples became galaxies. Galaxies birthed stars. Stars died and gave us the elements. And eventually from those elements came cells, breath, thought, consciousness, you. And now, as black holes merge and the universe continues to dance, you are part of the audience and part of the song, because gravitational waves don't just pass by, they pass through Earth, through matter, through you. Their frequencies are low, their movements subtle, far too gentle to feel, but they touch you nonetheless, like tides moving through the bones of the cosmos. LIGO hears these waves by measuring impossibly small changes in length, fractions of a proton's width, as light travels back and forth along laser arms. When a gravitational wave passes through, it stretches space in one direction and compresses it in another, like the surface of a pond trembling under a breath of wind. It is not the kind of sound we know. It is a deep tone beyond hearing, more felt than heard. A cosmic bass note. And with each detection, we learn more, not just about black holes, but about the nature of space-time itself. We begin to see the universe not as a static field of dots and structures, but as something alive with motion, alive with music. This is not a metaphor. The very equations that govern gravity, Einstein's field equations, predict that space-time behaves like a medium, that it can stretch and bend and ripple, and where there is vibration, there is song. Perhaps it's not so strange, then, to imagine the cosmos as a kind of symphony, each event a note, each wave a phrase, each burst of gravity, light or radiation, another line in a melody that spans billions of years. You might not hear it as music, but something in you resonates with it, because you are made of that same matter, held together by the same forces, shaped by the same laws. And if the universe has a rhythm, then your heartbeat is part of it. Not separate, not accidental, but echoing. That's why, when we detect these waves, it feels like more than data. It feels like discovery in the oldest sense. Not just of knowledge, but of belonging. We're not outside the universe watching it perform. We're inside it. Instruments in the orchestra, notes in the scale. When those black holes merged, 1.3 billion light years away, the wave they sent out passed through untold galaxies, stars, clouds of gas, fields of dark matter, and eventually through us. The wave didn't care, it didn't slow down. But we, fragile, quiet, curious beings on a small blue planet, caught it. And in doing so, we learned to listen. We'll go deeper into the idea of music in the next session, into string theory, where particles are not points but vibrations, where the universe itself might be nothing more than a great song played across hidden dimensions. But for now, just breathe. Feel the rhythm of your own body, the quiet rise and fall, the pulse behind your eyes, and know that even now, somewhere in the cosmos, two stars are spiraling, two black holes are drawing close, and the universe is preparing another note in a song that never ends. If the universe is a song, then what plays the notes? What hums beneath the surface of particles, planets, black holes, and you? For decades, physicists have sought not just to describe the universe, but to unify it, to find the thread that runs through gravity and light, atoms and emptiness. One idea, elegant and elusive, suggests that everything is made not of tiny dots or billiard ball particles, but of vibrations. Not things, but motions. Not objects, but strings. String theory proposes that at the smaller scales, far below atoms, far below protons, far even below quarks, there exist tiny one-dimensional loops of energy. These are not particles in the traditional sense. They are threads, vibrating in multiple ways, each mode of vibration corresponding to a different particle. A photon is a string vibrating one way, an electron another, a graviton yet another. The universe, in this view, is not built out of things. It is built out of tones, out of notes, out of tiny trembling patterns of motion. What makes this idea so profound is not just its poetry, but its necessity. When physicists tried to describe gravity and quantum mechanics in the same framework, contradictions emerged. The math refused to cooperate. But with strings, tiny vibrating loops instead of point particles, those contradictions softened. The mathematics began to sing in harmony again, but there was a cost. For the equations to work, space needed more dimensions. Not 3, as we experience daily, length, width, height, not even 4 if you count time, but 10 or even 11. Most of these extra dimensions, we're told, are not visible because they are curled up, tightly compactified, folded in upon themselves like delicate origami. They exist at scales too small to see, but they shape everything we do see. You might picture these hidden dimensions as tiny loops attached to every point in space, or as intricate geometric shapes tucked into every location in the universe, invisible but influential. Just as the strings on a violin resonate differently depending on their length and tension, the shapes of these curled up dimensions determine how strings vibrate, and thus which particles exist. The structure of space determines the music that plays. This brings us to a subtle but beautiful thought. That matter is music, and space is the stage. What we think of as stuff, rock, air, blood, flame, is not solid in the fundamental sense. It is vibration, movement, a symphony of tiny invisible strings playing themselves into being, and gravity. Gravity might be more than just curvature. In string theory, gravity arises naturally. One of the vibrational modes of the string is a graviton, a hypothetical particle that carries the gravitational force. Unlike other forces, gravity is extraordinarily weak. You can lift a paperclip with a fridge magnet, overcoming the gravity of an entire planet. Why is that? One explanation from string theory suggests that gravity may be weak because it leaks into these extra dimensions. It is not confined to the 3 dimensions we move through. It spreads thin, like a song echoing down unseen hallways. There's humility in this picture, that our entire universe may be a membrane, or brain, floating in a higher dimensional space, that we and everything we know are confined to this brain, while gravity slips between them all. The world we call everything may be only one slice of something far vaster, and the deeper structure of existence may be humming quietly, always just beyond reach. Some versions of string theory, such as T-theory, even suggest that strings are not the smallest entities, but that membranes of various dimensions, including 2-dimensional sheets, and higher may be the true fundamental units. These ideas are still in development, still debated, still tested against what we know. But they open a door, not just scientifically, but emotionally. They suggest that reality is layered, textured, resonant, that beneath the surface is a deeper pattern. And that pattern is not stillness, it is vibration. Imagine plucking a string in a dark room. You can't see the string, you can't touch it again. But you hear the sound, you feel the air shift. That's what string theory offers, a way to imagine the invisible not as absence but as song. The cosmos becomes a musical instrument, played not by a hand but by law, by form, by necessity. And you, your body, your thoughts, your dreams, are made of that music. You're not listening from the outside, you are one of the notes. It's a humbling vision, but also an intimate one. If true, string theory means that you're never truly separate from the universe. You are a resonance, a temporary arrangement of tones, a chord held in tension, shaped by curled dimensions, sustained for a little while before dissolving back into silence. And perhaps that's what black holes do too. They gather these resonances, they absorb the music of stars, of matter, of motion, and in time, through their radiation, they let it go again. Not in the same form, but not without meaning. In our next session, we'll bring all of this together, the ripples, the vibrations, the hidden dimensions, and explore the idea that space itself is not empty, that what appears to be nothing is actually structure, a lattice, a quiet weave of being. But for now, breathe in this idea: the universe is not made of things, it is made of motion, and everything you are, everything you know, is a single, gentle vibration in a grand, unfolding song. When you look into the night sky, it's easy to imagine that space is empty, that between the stars, between the galaxies, there is nothing but darkness and distance, a vacuum, vast and hollow, silent and still. But space, like silence, is never truly empty. It has a texture, a geometry, a responsiveness that speaks not in words or colours, but in how things move, how they fall, how they curve. What we call space-time is not a passive backdrop. It is a participant, a stage that bends with the weight of presence. Einstein showed us that mass curves space, and curved space tells mass how to move. But this curvature is not a metaphor, it's real. Space bends, stretches and compresses. Time dilates, stretches like honey when drawn from the spoon. And these aren't effects on top of some invisible scaffolding. They are the scaffolding itself. Space and time are not containers. They are the content, and perhaps even more than that. They are structured, not continuous and smooth as they appear from a distance, but stitched, woven, textured at a scale too small for even the sharpest instruments to see. Some physicists propose that space-time is made of discrete units, like a lattice or grid, not in the way of visible squares or cubes, but in the way that a fabric has threads. You cannot see the individual strands unless you look closely, but their interweaving gives strength, direction, flexibility. In the same way, space-time might be made not of smooth curves, but of countless interlinked loops. This is where loop quantum gravity enters, a theory that imagines space-time not as continuous, but quantized. That is, composed of tiny indivisible units, like atoms of geometry. Just as matter is not infinitely divisible, perhaps space itself comes in smallest possible pieces, woven together like a mesh. These loops would be unimaginably small, on the scale of the Planck length, a distance so tiny that it defies human intuition. But if they exist, then even the void is not nothing. It is form. It is structure. And what moves through that structure? Waves, disturbances, curvatures caused by the motion of mass. When a black hole forms, it presses into this mesh. When two black holes collide, they send ripples outward, not just through the illusion of emptiness, but through this hidden weave. Gravitational waves stretch and compress the lattice ever so slightly, sending signals through the body of the cosmos. These waves are not separate from space. They are space, briefly altered. It's helpful to think of space-time as something like a spider web, stretching across vast distances. The web is almost invisible in the dark, but when a drop of water falls on it, when something touches it, it trembles, it responds, it carries the motion outward in vibrations that move delicately along every strand. You, floating in the quiet of a sleeping room, may not feel those tremors, but they are there. And sometimes, when we build instruments with enough sensitivity, we can detect them. We can feel the tension in the web, and when we do, we learn what touched it, even from far away. But here is the deeper truth. You are not separate from this lattice. You're not sitting on top of it, or beside it, or drifting through it like a boat through water. You're made of it. Your body, your atoms, your heartbeat, your awareness. They are arrangements within space-time itself. You're not in the universe. You are of it. A localized pattern of energy and information, arising from the same structure that curves around stars, that folds into black holes, that sings when disturbed. When we say the universe is expanding, we don't mean that galaxies are flying through space. We mean that space itself is stretching. The lattice is expanding. New space is being added between things. The distance between galaxies grows not because they move, but because the web lengthens. It's like dots drawn on a balloon as it inflates, not moving across the surface, but carried apart as the surface stretches beneath them. And just as the web stretches, it also holds memory. Not in the conscious sense, but in the form of imprints. A gravitational wave passing through leaves behind a momentary distortion. A black hole's formation leaves behind a curvature. The universe remembers not with thoughts, but with shape. Not with stories, but with angles and arcs. And in that sense, every moment, every event leaves a trace. Stillness, too, is woven with motion. What feels quiet is often filled with unseen rhythm, like a violin string held still, but vibrating with the memory of its last note, like a leaf that appears at rest, but trembles in the current of air. The universe, even in its calmest spaces, is never truly still. It breathes, it shifts, it listens, and this texture, this quiet, fundamental weave, is the final foundation. Beneath particles, beneath vibrations, beneath time itself, there is a pattern. A structure that does not require observation to exist. That holds you even when you're unaware of being held. That sings softly, even when your ears are closed. In the final part of our journey, we'll reflect on what this all means. Not in terms of formulas, but in feelings, in wonder, in presence. We've fallen into black holes, crossed event horizons, imagined other universes, heard the songs of space-time. Now, it's time to rest in that knowledge, not as a conclusion, but as a soft invitation to sleep. But before we go, let this image rest with you, that everything, the stars, the space between, the black holes, the thoughts you're thinking right now, is a ripple in a vast woven stillness. And even the silence is made of motion. If you've made it this far, you've drifted through vastness, past the edge of gravity's grasp, across the quiet ripples of space-time, and into places where the known laws of physics begin to murmur and fold in on themselves. You've wandered among theories and textures, along the curved seams of existence, into the hush where time slows, stops, and perhaps loops back again. And now we're here, not at the end of the story, but in the soft stillness that follows wonder. Black holes may seem terrifying when first introduced. The name alone conjures something hungry, something final. But if we've seen anything tonight, it's that black holes are not monsters. They are not cosmic destroyers lurking in the dark. They are boundaries. They are the quiet punctuation marks in a sentence the universe continues to write. Not exclamation points, but ellipses, places where the story doesn't end but pauses, curves inward, waits. They are the most extreme expression of gravity. Yes, but not violence. They do not shred the universe, they shape it. They bend the paths of stars. They whisper in waves. They teach us gently about what it means to move through space, to stretch through time, to fall not as a failure but as a transformation. They are not the edge of understanding, but the invitation to continue, to listen deeper. And what do they say? Not with sound, of course, but with silence, patterned and slow. They tell us that the universe remembers, that every piece of matter that falls in, every photon that skims the edge, every ripple in the fabric, it all matters, even when it disappears from sight, even when it dissolves. It is not forgotten. It is folded, encoded, curved into the surface of something that speaks without words. You too are part of that conversation. You're not just watching the black hole from afar as if through glass. You're made of the same ingredients: star stuff, dust, vibration, and memory. You're the product of gravity's slow hands, of thermodynamic songs, of quantum whispers. You're a brief but vivid shape in the larger weave, and just by being here, by thinking, by wondering, you make the story more complete. There's something peaceful in knowing that black holes exist, that there are places where light cannot escape, where time stretches into stillness. That there are silences so deep they become form. That the universe, so often loud with heat and motion, also knows how to hold still, knows how to wait, knows how to fold a moment inward and keep it there, not lost, just quiet. And maybe that's what sleep is too. Not erasure, not absence, but folding. A moment of turning inward, a place where a memory doesn't vanish but reorganises, where thought doesn't stop but softens, where time bends slightly just enough for dreams to find their own strange rhythm. So tonight, as you close your eyes, you might imagine yourself not drifting away, but curling in, like light bending toward the horizon, like space folding inward around a presence, like a quiet black hole, silent, unseen, but meaningful. Maybe you're a small echo of the cosmos, a little pattern of gravity and heat and hope, a soft voice carried forward by time. Maybe the universe isn't something you're looking at from the outside, but something you're helping unfold from within. The black holes we explored aren't final. They're ongoing. They evaporate slowly. They speak in radiation. They may even give birth to new worlds. And just like them, you are part of something that continues, long after you stop trying to name it. So let go now. Let your thoughts slow. Let the shapes of the day recede. There's no urgency here. No edges. No collapse. Just the quiet hum of space-time and your small, vital part in its music. You've wandered among stars and singularities. You've folded space in your mind, bent time gently across your thoughts. You've stepped across horizons, whispered into other universes, listened to waves that ripple through the dark. And now all that remains is stillness. Sleep well, little fold in the sky. Sleep well, echo of the cosmos. The universe remembers.